Before we can do hypothesis testing, one of the first concepts we need to be familiar with is something called standard error, or standard error of the mean. To illustrate this, let's say that we're interested in a population of all the students at a university, and we have all of their weights plotted out here. Okay, we have some weights that are outliers over here, some that are outliers over here, and most of them clustered around a mean of 150 pounds, with a standard deviation of 8 pounds. Now, let's say that we build a sampling distribution where we sample a size of n, and n can be 16 in this example. So we take 16 students from this population, we take the average weight of all those 16 students, and then we plot that average down here on this histogram. If we do that thousands of times, an infinite number of times, we start to build up a sampling distribution that begins to approach normality. And importantly, the mean of the sampling distribution is the same as the population distribution on average. However, as you can see here, it seems that there's less spread in the sampling distribution. It's more clustered more tightly around the mean than it is in the parent population. This is because when we draw big enough samples from the parent population, we might draw one of the outliers over here in the sample, but we also would be gathering data from here, here, in the middle of the distribution, and maybe even one or two of these outliers down here. And the point is, when you average them together, they tend to cluster more centered around the true mean. If we do this enough times, then it's going to be even more tightly clustered around the population mean. So to calculate standard error, we just need a couple pieces of information. Standard error is defined as the standard distribution, or the standard deviation of the population mean divided by the square root of n, which is our sample size. So if we fill in all these blanks, we have a standard deviation of 8 divided by the square root of n, which is the square root of 16, which is 8 divided by 4, which is 2. So what the standard error is the standard deviation of this sampling distribution. And you can see that it's always going to be tighter and therefore less than the standard deviation of the parent population, which will be more spread out due to outliers. The sampling distribution mitigates this by averaging outliers together if they happen to be included in the sample and then plotting them down there. So, if we were to take our typical z-test where we only have one score, so for example, we want to see what somebody's percentile is on a standardized test. That's actually a special case of calculating the standard error from a sample. Only this time, our sample is 1. So we recall that the formula for a z-score is our score minus the population mean divided by the standard deviation. But if it's only a sample of size 1, this could be the same thing as a standard error of the mean, because all it is the standard deviation of the population divided by root 1, which is 1. It's going to be the same as the standard deviation of the parent population. Likewise, if we have a ginormous sample size of close to infinity, well, not really infinity, but close to the actual size of the population, it is going to be extremely tightly centered around the true population, the true mean of the population. That's because if we have a huge sample size and we keep sampling that over and over again, there's going to be virtually no variation from the true population mean. It's almost as though we're virtually sampling the entire population again and again if our sample size is large enough. So that's how you calculate the standard error of the mean, and that is conceptually what the standard error is. It's simply the standard deviation of your sampling distribution, which gets tighter the more people or observations that are in your sample.